Welcome to this live interactive session 6 of this NPTEL course, Advanced Transition Metal Organometallic Chemistry. I am Professor Ghosh of IIT Bombay, the instructor for this course, and along with me is Mr. A.P. Prakashan. He is the TA for this course. As usual, in this live interactive session, we are going to take up questions and queries that you may have after going over the 3 lectures that have been given. These are mainly in C7H7 ligands and their organometallic complexes. Since there is no offline question for me right now to take them, request you to send us your queries during this live session, and I would be happy to answer them as I receive them. Please send us your queries based on what has been covered in this week, and we would answer them as we receive them. The lectures in this week had mainly been on C7H7 ligand, which are used as organometallic ligand for binding to transition metals. We have covered the various methods available for synthesizing this organometallic C7H7 ligand-based complexes, their structures as well as their reactivity, and compared them with respect to the parent or the original C5H5 ligands to see how they comparatively fare in these series of organometallic transition metal complexes. Please request you to send us your queries, and we will be answering them as we receive them. There aren't too many people present in today's live session, it seems. We'll wait. Okay, here is a question from ML Naidu that says why mixed complexes C5, H5, MC7 are more stable than C6, H6, M, C6, H6 complexes. Actually, Mr. Naidu, the stability sort of comes from the electron count or the valence electron count that would involve the counting the metal valence d electrons as well as the ligand electrons, and there is no generic trend that the mixed are more stable than the neutral ones. For example, in this the stability as such is something that is dependent on the total valence electron or electron configuration of the metal complexes, as well as the steric and the electronic demands. Now, in the two complexes that you have quoted, one is C5H5 M C7H7. versus C6H6M, C6H6. Now you see that in the first one there is an anionic ligand. C5H5 is an anionic ligand bound to a cationic metal fragment, as well as C7H7 also is a anionic. It can bind in a cationic form. The binding of anionic ligand to a metal center will be more stronger than when it is binding in the neutral form, and in that way you can say that the metal complexes containing C5H5 unit is slightly more strongly bound than a metal binding to C6H6, which are neutral pi-electron ligands. So let me just recapitulate what I just said. What it says that the stability is a function of their electronic and steric unsaturation. Electronic unsaturation will be defined by how far off they are deviated from total 18 valence electron rule, and as well as what kind of steric demands the ligands are imposing on the metal. And there cannot be anything which is generic as to say that mixed ligand complexes are always more stable than the homoleptic metal complexes. There is no such generic rule. However, in the complex that you have quoted, C5H5 is binds as a cyclopentadienyl anion, and as a result of which this being anionic ligand binding to metal complex, they bind more tighter than a neutral ligand would bind to the same metal cation. So in that perspective, one can say that C5H5 moiety binds more strongly to the metal. So I think I have answered your queries as explicitly as possible. I hope this satisfies your question. Please send us if you have any other question. Oh, please. Here is another question from Mr. Naidu. Please explain the mechanism of iodination on CP ring at lecture 31 at 1858. Is it followed by a stelic coupling? So as we talk, we'll go back to the reference that you have given, and then we'll come back to you as we get hold of the slide and the time in which of the lecture we have just said. 18 butyl lithium, then can you just open it? No, this is C7 CP mixed CP ligand. The first one, the iodination happens. Yeah. What is this? C4. This is CF4 I2. So this will give us iodine electrophile. Alkyl halide, but usually no, but this alkyl halide. Over here the iodination happens first by lithiation, so you make an anion, and then this C2F4I2, and then that gives a iodine cation. So it's just the iodination with help of iodination with the help of butyl lithium followed by I plus reagent, and that gives the iodide, and after that it's a simple steely coupling that is affected by the tin alkyne reagent in presence of palladium as the coupling metal. So yes, it is iodination resulting from lithiation followed by treatment with diiodotetrafluoroethane. Exposes iodine I plus because there are four fluorine, which will be electron pulling, making the carbon electronegative. As a result, the iodine leaves as I plus, and then that gets lithiated. Reacts with the lithiated Cp to give the iodination. So I think I've answered your question, and followed by this steel coupling, that is the tin reagent in presence of palladium. Hope this answers your question. Yes, the second part is steel coupling, as you rightly said, and the first part is iodination with butyl lithium, lithiation followed by I plus addition against the lithium reagent using that tetrafluorodiiodide ethane complex. So, what is the mechanism of light in the CO cleavage from metal complexes? Is it a radical mechanism? What is it? Usually, say when a no, it is not a radical mechanism. Okay, to answer you right away, CO binds to metal by virtue of two electrons being donated from the carbon onto metal. Now, when the CO dissociates from the metal in presence of light or heat, the CO dissociates as a CO molecule, taking back both of the two electrons that it had donated to the metal. So as a result, the metal possesses a vacant site because that site no longer is occupied by two electrons donated by the CO ligand, and CO comes off as a CO molecule, having electrons that it had donated. So there is no question of radical formation due to CO cleavage from a metal complex. So hope I've answered your question. There is absolutely no radical formation. It's just the carbon monoxide which binds to metal cleaves off in presence of light. Please send us your query. Please send us your query. We have been asking some very interesting questions, Mr. Naidu. Lecture 32 at 1714 equations are not balanced. Titanium compound 0.1 mole, but the product is 1 mole equivalent. Mr. Naidu, some doubt over the second equation that aluminum compound a reducing agent for the reaction. Let us, as you said, we just got to your question. Now we are referring back to the slides that you have referred us to go back, and then after we see the slides, we'll come back to you and answer the question. TATG. Into are they balanced? He said they are not balanced. Huh?
Then this is 0.2 and this is 0.4 but the product is 1 mole.
1 mole is 2 equivalents.
Then this is 0.2 and this is
Okay, what is the question? Can we see the lecture? The equations are not balanced. Yes, it's true. The equations are not balanced, as has been rightly pointed out. And what it says that depending on the stoichiometry, of the reactant, they could get complexes in which there are 2 ligands bound versus 3 ligand bound. That is in a monometallic or bimetallic metal center. So these reactions are not balanced, and what does that mean? That the product is not the only product which may be forming in a particular chemical reaction as has been designated. So there may be other side products which may also appear along with the main product which has been shown, and that is why it is not balanced, and that's how it's been given in the textbook. I believe the primary reason the textbook wants to highlight is the fact that by varying the metal as well as by varying the ligand stoichiometry, one can make different compounds of different formulations having one single metal center or bimetallic complexes with 2 or 3 C8H8 ligands. So it is to highlight that these two equations are quoted. Now, what is your second doubt is that the aluminum compound is a reducing agent for this mechanism. Yes, it's looks obvious from here that titanium, which is in +4 oxidation state in the reactant, ends up becoming these are 0 titanium 0 complexes. Yes, the aluminum over here have been used as a reducing agent, as you have rightly pointed out. I think that clearly clears your doubt. Now, there is third question that I see from here end, which says that is there any application for sandwich complexes in catalysis? Yes, there are like bis cyclopentadiene titanium complexes, titanium X2 complexes, are used in olefin polymerization reactions, making polyolefin, and there are a host of other reactions that catalysis that these cyclopentadienyl complexes do. So I would refer to you a nice review by Paul Chiric, the editor-in-chief of Organometallics, who has written a nice article on group 4 transition metal sandwich complexes in catalysis. So that would give you a fair amount of nice perspective. This is a 2010 Organometallics review. We are going to SMS you in the chat. We are going to SMS you the reference. You can look up to see what kind of catalytic applications these sandwich complexes have. And one primary thing is in olefin polymerization that I had just mentioned. Apart from that, there may be other catalysis where they would be useful. So request you to refer to this article by Paul Cherick on the applications of transition metal sandwich complexes in various forms of catalysis. Please, that was a very nice question, Mr. Naidu. Please send us some more, and we have also referred to you this particular article, which we think that you may find useful with regard to the applications of transition metal sandwich complexes in catalysis. At 29:30 of the lecture 32, can you please explain the formula of the complex? Yes, well, thank you for bringing that over to us. We are going back to the lecture at the time instance which you have mentioned, and then we're going to get back to you with the answer. What is the question? The question says, can you please explain the formula of the compound? Okay, so this is cyclooctatetraene, no? Cyclooctatetra. Yes. So let us. This is very clear. If you see that there is at the center there is a in a 8-shaped, which is in a conformation which is a skewed boat kind of, which is flipped over, and this cyclooctatetraene tetraene ligand with its butadiene moiety is bound to titanium and then to another C8H8 ligand, when the other side is also bound to another titanium with CH88 ligand. So actually the two titanium centers are there. It's a bimetallic compound. One titanium center is bound to C8 in eta 8 fashion with CH88 ligand, another to in a 1 to 4 or eta 3 fashion, whereas the second titanium is also bound to C8H8 ligand in a eta fashion, and then to the half of the 3 to 6 eta atoms of the middle C8H8 ligand. I would refer you to this Ershenberg organometallic textbook, page 556, where this diagram is drawn more explicitly, or to the class note. I think class note is fairly clear, but since I've drawn the structure by hand, it may not look good. So I refer to this Ershenberg book, page 556, where this diagram is more clearly explained. This is a third edition of the book. So there are two titanium. Each of them is bound in a eta 8 fashion to C8H8 ligand, and the third CH88 ligand is sort of bridging between two titanium center. Half of it is bridging to one titanium, and the other half is bridging to the other titanium. Let me put it that way to be more simple. Sir, why no late transition metal group 11, 12 complexes were discussed? Metal resistance with CPU. Well, see, if you look at these metallocene complexes, for example, like up to iron for 3D, you would see that the 18 valence electron would be forming up to iron. The post iron nickel, it becomes a 20 electron system, and then if you go further, let's say for copper and zinc, then it will the electron count will even shoot up higher. So what does that supposed to mean? That supposed to mean is that till nickel there are examples where they can be isolable, they can be used, whereas the metallocene, as per se, we're having two cyclopentadienyl ligand for the group 9 and 10. Those may not be very stable, and may not also be isolable. That is the reason why they were not taken up. Also, I must say that these metal complexes having more than 18 valence electrons are only possible for 3D transition metals, whereas if one goes to 4D and 5D series, then 18 valence potential metal complexes of 4D, 5D having more than 18 valence electron becomes almost non-existent. So having said that, up to nickelocene, which has about 20 valence electrons, which is even higher than that of ferrocene, which has 18 valence electron. These are very stable and obtainable and isolable, and hence have been discussed. And beyond 20, they are not that isolable or not that stable, and as a result, they are not encountered so frequently, probably non-existent also, and because of which they have not been covered. So hope I have answered your queries. Please send us some more questions. You have been having some very interesting session. Just 0% coverage. CP is NDC CP2 is EFT. Not even there. Please just see the abstract. What is EFT? Please send us some more questions. These have been some very interesting questions that you've been asking. Please send us some more questions. Actually, the other thing regarding another question we have, why does lithiation happen at CP ring in case of vanadium and the cyclopentadiene ring in case of titanium for mixed cycloheptanyl sandwich complexes? Okay, we'll get back to you as we pull out the pages. The cyclopentadienyl, heptatrianyl, vanadium. Vanadium, CP ring in vanadium and cycloheptatrianyl ring in titanium. Which one? Oh.
Lithiation is this one.
Okay, and
Okay, this is
the also reaction conditions available also for dilithiation. Okay. For what chemistry also depends on the metal center. Actually, see, we in one case in titanium, what we see that lithiation happens on the seven member ring first, whereas in case of vanadium, the lithiation happens in the 5-member ring. There is no absolute convincing reason to explain this trend, possible trends that you have just mentioned, and what has been observed that these are very much dependent on the metal in which the metal of this transition metal complexes. For certain metal, it is one of the 7-member rings get lithiated, and for the other the 5-member rings get lithiated. And if one goes to harsher conditions, then probably both of the rings can be affected through lithiation. So I would refer you to the same page number 554 of the same book, Eastern Boy, where it says that there is no absolute exact reason as to why this is happening, except to say that certain metals, for certain metal complexes, the lithiation at one site is more preferable over other metal complexes where the lithiation happens at the other ring site. So request you to refer to page 554 of this Estenboy 3rd edition book for detailed discussion on this. Can you just send this thing? At 5094, is that a heterocomplex diamagnetic or paramagnetic? We'll get back to that. Okay, so if it is this is 3 plus 1 4, and then iron is what? Say 6 8, no? 8 plus 4 12, 12 plus 6. So yes, the iron itself is 18 valence electron compound. As far as the rhodium, what we see is rhodium 4 plus 1 5, 5 plus 9 14, and 2 18. So if you I would refer you back to the discussion, and you see that both iron and the rhodium center have 18 valence electrons each, and you can do the electron counting as has been explicitly done in the slide, and then you would see that if they are 18 valence electron compounds, they are obviously diamagnetic in nature. So to answer your query, both the overall compound is diamagnetic, and each of the metal center has 18 valence electron compounds. Hope this satisfies your answer. Then at 25, why showing H plus bonding interaction is important. We'll get back to that. This is at 25, 2509. Oh, this one. What is the question?
Why the hydrogen bond is incomplete?
Okay, so when reacting with okay, yes. See, now that's a very interesting question. Now, if you look at this reaction, FeCl2 is reacted with Me4C4 nitrogen minus lithium plus. So now, if on a first, in a more conceptual way, you would have thought, or one may think that the nitrogen being anionic in nature would replace the chlorine of FeCl2 and make a nitrogen bonded nitrogen iron bond, and then this C4H4Ma. So it would be a simple sigma bond from nitrogen onto chlorine of the iron. But the structure obtained is not so. What the structure obtained shows that the iron is in fact binding to the C4 Me4 nitrogen heterocycle through the pi ring cloud, and the nitrogen and there is another surprise over here. The nitrogen it does not stay anionic. It gets protonated and picks up a proton which is sort of hydrogen bonded and stabilized by another anionic moiety. So yes, the hydrogen bonds sort of prevents the nitrogen lone pair or sort of nitrogen sort of stabilized lone pair gets stabilized by weakly interacting with a proton through a hydrogen bond interaction, and hence the nitrogen lone pair is not available for binding directly to iron for making the FeCl2 complex. Iron makes a bis sandwich as a ferrocene type of complex where iron binds directly to the pi cloud. So that is the role of hydrogen bonding in predicting a structure which is different from what one would be intuitively arriving at if they just look at the charge balances in that given equation. Hope I have answered the question. If is TMEDA tetramethyl ethylene diamine beta lithium, obviously this one has to see in a very simple way. One explanation would be beta lithium is a carbon ion, and TMEDA is a neutral anion. So being anionic and carbon ion in nature, beta lithium is expected to be a better base than TMEDA. Let's see the PK. PK of TMEDA, PK of beta lithium. PK is about 10.4 for go to the previous PK, previous slides. The second line. Second topic, yeah, 10.4 pKa 10.40. Okay, 24 degrees. And beta lithium pKa would be okay. That one. No, not this one. This doesn't have beta lithium, does it? Hmm. Increase it, go to some other place. 53. So beta lithium is so very basic, 53, whereas TMEDA is 10. So obviously beta lithium is much more basic than TMEDA. And this you don't have to get the pKa number, but you can only guess that beta lithium being anionic, it's expected to be a better, more basic than TMEDA, which is neutral. Hope I have answered your query on TMED and butyllithium. Butyllithium has a pKa of 53, which is so very basic, as opposed to TMEDA of 10. But you don't need these pKa numbers. You can sort of get them from their just anionic and neutral form. But even is 10, no? Let's verify that. 53 would be more basic. Please send us your queries. You have been sending some very interesting questions, Mr. Naidu. Please send us some more queries that you may have. Just confirm it independently for some values. Which organometallic discovery would deserve Nobel Prize next? Okay, that's a very interesting question, and if I could answer that, I can always try to explain many of them, but you know, let me just put it this way: that there may be several discoveries which may be worth the Nobel Prize, but the one that will really make it are not a simple decision, and these are at times like being at the right time at the right place, that the award is conferred. Uh, so we have seen organometallic chemists getting Nobel Prizes for various reactions like hydrogenations, olefin polymerization, metathesis, olefin metathesis, so on and so forth. which deserves mention. But at this point, it is not, as well as for the as recently as the cross-coupling reactions, which have attracted attention. However, having said that, it is not very obvious or very simple to just predict something regarding as to what will be the next Nobel Prize winning discovery, and that is not limited only to the intellectual acumen about of the discovery, but also to the practical purpose it serves, and also to its utility to the society, which poses a much larger question, and then it may not be that easy at this point to predict which organometallic discovery would get the next Nobel Prize. Personally, on a personal note, I would rather like to see N-heterocyclic carbines being awarded a Nobel Prize for their versatility in catalytic applications as a class of ligand in catalysis. I would also like to see therapeutic usage of organometallic compounds being recognized through Nobel Prize, because as one of the next big discoveries in the area of organometallic chemistry. But these are my own preferences, my own thoughts. I'm not sure whether they would materialize, or they would be award, like they would see the light of the day in terms of winning Nobel Prizes. Please send us some of your questions. We'd be happy to answer them as we receive. Please send us your queries. What's an example of PD4 plus PD2 catalysis cycle? Are they feasible to undergo? Okay. There are, this is see, there are this is a very relevant question. Most of the cross-coupling reactions that has that people refer to, they mostly go through palladium 2, palladium 0 cycles. However, there are certain certain transformations, cross-coupling reactions, which people have also referred to be going through palladium 4, palladium 2 cycles, and then those are but much rarer in nature with respect to palladium 2, palladium 0. However, there are at this point I can only say that there are few cycles which are palladium 4 and palladium 2 in the literature. The middle one, no, below, just below, like left, right, this one. So no, uh, maybe this one, this the before one, left one, maybe. Uh, by and large, it is very understandable when you say that oxidative additions are more prone to be occurring on palladium 0, palladium 2 cycles than on palladium 4, palladium 2 cycles. But then I would refer to some existing literature on the same. However, at this point, I do not have examples where I can refer to palladium 4, palladium 2 cycles mm, for these oxidative addition reactions. Uh, hmm?
Which other one is in the definition of palladium 4 cycle?
Yeah, sure.
Which
Is your paper? Now, the oxidative addition, even if it's happening, may be less likely or more difficult in case of palladium 4, palladium 2 cycle. That is what, at this point, I would explain, answer with respect to the question that you have asked. But by and large, to the extent that we have covered most of them are palladium 0, palladium 2 cycles where oxidative additions would be the first step of the reaction. Hope I have answered your query. Now let us see if you have any other questions. Is there any questions? No. Nobody, if somebody gives, there is 1 million. To answer your last question, I do not have offhand right now a ready example of palladium 4, palladium 2 cycle. However, there is a school of thought, however less popular, but there are certain cross-coupling reactions which are believed to proceed by palladium 4, palladium 2 cycles. Request you to refer to those literature for more thorough detailed study. Please ask more question. We are coming towards an end. We only have about 5 or so minutes remaining for the end of this session. So request you to send us your query as quickly as possible. See? Is butyl lithium an organometallic compound? I know where this question is coming from. You want to specify on the ionic nature. Yes, butyl lithium is an organic metallic compound. To answer more explicitly, see, organometallic compound would contain a metal carbon bond. This bond can be covalent, this bond can be ionic, and they would all belong to the larger family of organometallic compound. Now, the classification of organometallic compound we have given in elaborate details in our first organometallic course, which was the course that was run on last semester. And for you to read it in detail, we refer you to this the discussion again in Ashton Boyd that gives the various classifications of organometallic compound based on the polarity. So refer you to page 11 for various kinds of organometallic compounds. Some of them are ionic, some of them are covalent, to see what variety of organometallic compounds exist. So there is a definitive treatment given on various types of organometallic compound in our earlier course, which was transition metal chemistry, organometallic compounds from principles to applications. And you can also refer to the book, Sternberg book, page 11, where discussions of various kinds of organometallic compounds are given. So request you to refer to the book. Okay, for classifications of organometallic compound. Okay, is calcium carbide organometallic compound? Okay, is calcium carbide okay, calcium carbide is salt. Is it? It's a salt, and over here, this the carbide is just a bare carbon surrounded by calcium, and it has a structure of itself. Now, these I'm not sure whether to call it a organometallic compound or not. To answer you honestly, uh, like whether it will be classified as yes, probably by definition it will, but it is one of the not certainly not a very representative examples of organometallic compound. At least that is what at the most I can say. Calcium carbide is also, you see, known as calcium acetylide, and acetylide moiety of a metal would be organometallic compound, and from that instance, one can say that this would be within the larger family of organometallic compound. If you look at the formula, this is C111C with dianion bound to calcium 2 plus, and hence since it is a dianion of acetylide moiety, metal acetylides like in Sonagashira coupling, our copper acetylide is organometallic compound. From extension of that, we can say that this would definitely fall in the larger group of ionic organometallic compounds. What is the question? Graphite, intercalation, organometallic compounds. Okay, okay. Now, for graphite, I would not call them intercalation organometallic compounds. First of all, intercalation of a metal in graphite is not a compound. What would be a compound? Compound would be some, it does not fall in the definition of a compound. The intercalation of a graphite is more of a doping, where graphite gets doped, but they never make a compound. So actually, a graphite intercalation does not fall in the category of a compound. So from that instance, it will not be qualified as a compound. Graphite intercalated metal is not a compound in the first place. Hence, it cannot be qualified as an organometallic compound because it is not a compound in the first place. Anyway, it's just a metal doped inside several layers of the graphite. Hope I have answered your query. For the last question, yes, graphite intercalation is acetylides. From that, what would be a different property? Organometallic compound, what is the different property? No. But when you say there is a definition that ionic organometallic compounds or compounds are not. They are ionic organometallic compounds. They may show some coordination properties. Are silicons organometallic compound, given that silicon is a okay, silicons would be organometallic compounds of main group elements. They would be let's say they would be of main group elements. Now, main group elements may be metal, non-metal, like metalloid or metal-like. From the larger dimensions, one can still say of main group, like metal alkyls of main group element. From that perspective, one may study those. Okay. So yeah, thank you for your time, Mr. Naidu. It has been nice interacting with you, and we have come up with some very interesting questions. We have finished our stipulated time of 60 minutes for this live interactive session, and I thank you for patiently being with us and asking us questions that you have had from the previous lecture. Thank you for your time, and I look forward to being with you again in the next live session, which will be live session 7, same time, same place next week. That is next Tuesday at 3 p.m. I look forward to being with you till next week. Until then, goodbye and thank you.